Children, welcome to today's lesson about motion. In our previous class, we described the motion as the continuous change in the position of an object. We studied that the motion involves two types of measurements of length, one which depends on the endpoints of motion, that is displacement, and the other which depend on all points of motion, that is distance. Distance motion ਦੇ ਮੈਗਨੀਟਿਊਡ ਨੂੰ ਪਥ ਦੀ ਉਸ ਲੰਬਾਈ ਦੇ ਰੂਪ ਵਿੱਚ ਦੱਸਦਾ ਹੈ ਜੋ ਵਸਤੂ ਨੇ ਗਤੀ ਦੌਰਾਨ ਤੈਅ ਕੀਤੀ। ਜਦ ਤੱਕ ਵਸਤੂ ਚਲਦੀ ਰਹਿੰਦੀ ਹੈ ਦੂਰੀ ਵੱਧਦੀ ਰਹਿੰਦੀ ਹੈ। Magnitude of the displacement is equal to the linear distance between initial and final positions along the straight line joining two positions. Displacement of an object in between 2 points is the shortest distance between these 2 points. Distance and displacement have the same units. Displacement of an object may be positive, negative or 0, but the distance is always positive. Displacement is either equal to or less than the actual path length. Displacement does not tell exactly how the object actually moved between the two positions. One major difference between distance and displacement is that the displacement has direction also. Uniform motion ਨੂੰ describe ਕਰਨ ਲਈ ਅਸੀਂ average speed ਨੂੰ rate of motion ਵਜੋਂ ਲੈਂਦੇ ਹਾਂ। ਇਹ object ਦੁਆਰਾ distance cover ਕਰਨ ਲਈ ਲਏ ਗਏ time ਦੀ ratio ਹੈ। Average speed ਤੋਂ ਬਾਅਦ ਅਸੀਂ ਇੱਕ ਹੋਰ useful quantity average velocity ਤੇ ਵਿਚਾਰ ਕਰਦੇ ਹਾਂ। Average velocity ਕਿਸੇ object ਦੀ change of displacement ਦਾ time rate ਹੈ। Main similarities and differences between the average speed and average velocity are: average velocity of an object may also be defined as its average speed in a particular direction. Average speed of an object in a particular direction may also be defined as the magnitude of average velocity. Speed is always positive, it can never be negative, whereas velocity can be positive or negative. Speed of an object gives only quantitative knowledge of how fast the object is moving. It tells nothing about the direction of motion, whereas the velocity gives the complete knowledge of the motion as how fast the object is moving and in which direction is it moving. Speed and velocity both have same SI unit as meter per second. Non-uniform motion ਜਾਂ accelerating motion ਨੂੰ ਇਸ ਤਰ੍ਹਾਂ ਕਹਿ ਸਕਦੇ ਹਾਂ ਕਿ ਜਦੋਂ ਕਿਸੇ ਵਹੀਕਲ ਦੀ ਵੈਲੋਸਿਟੀ ਬਦਲਦੀ ਰਹਿੰਦੀ ਹੈ ਇਸ ਨੂੰ ਐਵਰੇਜ ਐਕਸਲਰੇਸ਼ਨ ਕਹਿੰਦੇ ਹਨ। ਸਰਲ ਸ਼ਬਦਾਂ ਵਿੱਚ ਐਵਰੇਜ ਐਕਸਲਰੇਸ਼ਨ ਸਮੇਂ ਦੇ ਨਾਲ ਵੈਲੋਸਿਟੀ ਵਿੱਚ ਪਰਿਵਰਤਨ ਦੀ ਦਰ ਹੈ। ਅਸੀਂ ਇੰਸਟੈਂਟੇਨੀਅਸ ਵੈਲੋਸਿਟੀ ਅਤੇ ਇੰਸਟੈਂਟੇਨੀਅਸ ਐਕਸਲਰੇਸ਼ਨ ਨੂੰ ਇੰਸਟੈਂਟ ਟਾਈਮ ਉੱਤੇ ਐਵਰੇਜ ਵੈਲੋਸਿਟੀ ਅਤੇ ਐਕਸਲਰੇਸ਼ਨ ਕਹਿ ਸਕਦੇ ਹਾਂ। Today we will derive equations describing the motion of an object moving with constant acceleration. Before going in details, let me share the learning objectives for today's lesson.
On completion of this topic, learners will be able to define motion, define rectilinear motion, define velocity and instantaneous velocity, define acceleration and average acceleration, discuss the vector nature of acceleration. State the kinematics equation relating initial velocity, final velocity and acceleration for a uniform motion.
Next step is to derive the equations of motion. Equations of motions ਨੂੰ daily life ਵਿੱਚ ਵਰਤਿਆ ਜਾਂਦਾ ਹੈ। ਜੇ time ਦੇ ਨਾਲ acceleration ਬਦਲਦਾ ਹੈ ਤਾਂ motion ਜ਼ਿਆਦਾ complex ਹੋ ਜਾਂਦਾ ਹੈ ਅਤੇ ਇਸ ਨੂੰ ਸਮਝਣਾ ਹੋਰ ਮੁਸ਼ਕਲ ਹੈ। ਇੱਕ common ਅਤੇ simple dimensional motion ਉਦੋਂ ਹੁੰਦਾ ਹੈ ਜਦੋਂ acceleration ਸਮਾਨ ਹੋਵੇ। ਉਦਾਹਰਣ ਵਜੋਂ without air resistance atmosphere ਵਿੱਚ ਡਿੱਗ ਰਹੀਆਂ ਵਸਤੂਆਂ ਦਾ acceleration constant ਹੁੰਦਾ ਹੈ। ਜਦੋਂ acceleration constant ਹੁੰਦਾ ਹੈ ਤਾਂ average acceleration instantaneous acceleration ਦੇ ਬਰਾਬਰ ਹੁੰਦਾ ਹੈ ਅਤੇ ਸੰਪੂਰਨ ਗਤੀ ਦੇ ਦੌਰਾਨ ਸਮਾਨ ਦਰ ਤੇ velocity ਘਟਦੀ ਜਾਂ ਵੱਧਦੀ ਰਹਿੰਦੀ ਹੈ। ਅੱਜ ਅਸੀਂ constant acceleration ਵਾਲੇ ਗਤੀਸ਼ੀਲ ਕਣਾਂ ਲਈ ਗਤੀ ਦੇ ਸਮੀਕਰਨ ਕੱਢਾਂਗੇ। ਇਹਨਾਂ ਸਮੀਕਰਨਾਂ ਨੂੰ equations of motion ਕਿਹਾ ਜਾਂਦਾ ਹੈ। ਕੀ ਤੁਹਾਨੂੰ average acceleration ਦਾ expression ਯਾਦ ਹੈ? ਇਹ time interval ਉੱਤੇ velocity ਦੇ ਬਦਲਾਵ ਦੀ ਰੇਸ਼ੋ ਹੈ ਜੋ ਕਿ vf minus vi upon tf minus ti ਹੈ। ਇਸ ਨੂੰ vf minus vi is equal to a times tf minus ti ਲਿਖਿਆ ਜਾ ਸਕਦਾ ਹੈ। ਇਸ ਲਈ vf ਬਰਾਬਰ ਹੈ vi plus a times tf minus ti ਦੇ। ਇੱਥੇ ਇਨੀਸ਼ੀਅਲ ਅਤੇ ਫਾਈਨਲ ਸਮਾਂ ਆਰਬਿਟਰੇਰੀ ਹੈ। ਸਰਲਤਾ ਲਈ ਮੰਨ ਲਵੋ ਇਨੀਸ਼ੀਅਲ ਟਾਈਮ ti ਬਰਾਬਰ ਹੈ 0 ਅਤੇ ਇਨੀਸ਼ੀਅਲ ਵੈਲੋਸਿਟੀ vi ਬਰਾਬਰ ਹੈ u। ਫਾਈਨਲ ਟਾਈਮ tf ਬਰਾਬਰ ਹੈ t ਅਤੇ ਫਾਈਨਲ ਵੈਲੋਸਿਟੀ vf ਬਰਾਬਰ ਹੈ v। ਤਾਂ ਇਸ ਇਕੁਏਸ਼ਨ ਆਫ ਮੋਸ਼ਨ ਨੂੰ ਲਿਖਿਆ ਜਾ ਸਕਦਾ ਹੈ v ਬਰਾਬਰ u plus at ਦੇ। ਇਹ ਵੈਲੋਸਿਟੀ ਦਾ ਸਮੇਂ ਨਾਲ ਐਕਸਪ੍ਰੈਸ਼ਨ ਹੈ। ਇਸ ਨੂੰ ਵੈਲੋਸਿਟੀ ਟਾਈਮ ਰਿਲੇਸ਼ਨ ਕਹਿੰਦੇ ਹਨ। ਇਹ ਫੰਕਸ਼ਨ ਸਾਨੂੰ ਕਿਸੇ ਸਮੇਂ ਤੇ ਵੈਲੋਸਿਟੀ ਨਿਰਧਾਰਤ ਕਰਨ ਵਿੱਚ ਮਦਦ ਕਰਦਾ ਹੈ ਜੇਕਰ ਇਨੀਸ਼ੀਅਲ ਵੈਲੋਸਿਟੀ, ਐਕਸਲਰੇਸ਼ਨ ਅਤੇ elapsed time ਦਾ ਸਾਨੂੰ ਪਤਾ ਹੋਵੇ ਤਾਂ। To show how it helps, let us try some numerical problems based on this relation. A ball is thrown straight upward with an initial velocity of 8.2 meter per second. If the retardation of the ball is 9.8 meter per second square, then what would be the velocity after 0.5 second? On substituting the value of t, that is 0.5 second, initial velocity u equals to 8.2 meter per second and acceleration a equal to minus 9.8 meter per second square. We get v equal to 8.2 minus 9.8 multiplied by 0.5, which gives v equal to 3.3 meter per second. In the same problem, what would be the velocity after 2 seconds? On substituting the value of t, that is 2 seconds, initial velocity u equals to 8.2 meter per second and acceleration a equal to minus 9.8 meter per second square. We get v equal to 8.2 minus 9.8 multiplied by 2, which gives v equal to minus 11.4 meter per second. Here negative sign shows that the motion is in downward direction. Next problem is, if a car initially at rest accelerates uniformly to a speed of 144 kilometers per hour in 20 seconds. What would be the acceleration of the car? Here, initial velocity of the car is 0 and after 20 seconds, final velocity becomes 144 kilometers per hour, that is 40 meters per second. On substituting the given values in the velocity time relation, we get 40 equal to 0 plus 20 times a, that is a equal to 2 meter per second square. In the same problem, if sudden brakes are applied and the car comes to rest in next 8 seconds with uniform deceleration, what would be the deceleration of the car? Here, initial velocity of the car is 40 meters per second and after 8 seconds, final velocity becomes 0. On substituting the given values in the velocity time relation, we get 0 equal to 40 plus 8 times a, that is acceleration, a equal to minus 5 meter per second square. Therefore, deceleration is 5 meter per second square. Our next problem is an automobile company claims that its deluxe sports car will accelerate from rest to a speed of 42 meter per second in 8 seconds. Under improbable assumptions that the acceleration is constant, determine the acceleration of the car. It is to be noted that initial velocity of the car, that is u, is 0 and after 8 seconds, final velocity, that is v, is 42 meter per second. On substituting the given values in the velocity time relation, we get 42 equal to 0 plus 8 times a, that is acceleration, a equal to 5.25 meter per second square. I hope the importance of velocity time relation is clear to you. Next, how far does the particle move in a given time if its acceleration is uniform? To describe this, let us recall the relation for average velocity. Average velocity is the time rate of change of displacement of an object or displacement per unit time, that is xf minus xi upon tf minus ti. This can be rewritten as xf minus xi equals to v average times tf minus ti, or xf equal to xi plus v average times tf minus ti. In fact, this relation is applicable whether the acceleration is constant or not. For the case of constant acceleration, this relation can be modified by obtaining the relation for average velocity in terms of initial and final velocity. If in the elapsed time velocity change linearly, then average velocity during this time is simply the average of initial and final velocities. That is, v average is equal to the sum of initial velocity vi and final velocity Vf divided by 2. On substituting the value of average velocity in the obtained relation for position, we get xf equal to xi plus half of the sum of vi and vf multiplied by tf minus ti. On substituting the value of vf from the velocity time relation, this relation for position becomes xf equal to xi plus tf minus ti by 2 into vi plus vi plus a into tf minus ti. This gives xf equal to xi plus vi times tf minus ti plus half a into the whole square of tf minus ti. This is the equation for measuring position. For convenience, let the initial time ti be equal to 0 and initial velocity vi equal to u. Final time tf be equal to t and final velocity vf equal to v, and let xi equal to x0 and xf equal to x. We can rewrite the relation as x equal to x0 plus ut plus half at square. This shows that the position of an object at any time t has quadratic dependence on time. When the particle moves with uniform acceleration along a straight line. This is the relation for position as a function of time, hence it is known as position time relation. If s is the displacement of the particle in time t, then x minus x0 is equal to s, and the general relation becomes s equal to ut plus half at square. This function helps us to determine the position at any time if initial velocity, acceleration and elapsed time are known. To show how it helps, let us try some numerical problems based on this relation. In our last problem, an automobile company claimed that its deluxe sports car would accelerate from rest to a speed of 42 meter per second in 8 seconds, with an assumption that the acceleration would be uniform. You have to measure the distance travelled in the first 8 seconds. It is to be noted that initial velocity of the car, that is u, is 0, and after 8 seconds final velocity, that is v, is 42 meter per second. Let the origin be at the original position of the car so that x0 equal to 0. On substituting the given values in the position time relation, we get x equal to half of the sum of 0 and 42 multiplied by 8, that is x equal to 168 meter. Our next problem is a car racer starts from rest and accelerates at 7.4 meter per second square. how far it would travel in 1 second. It is to be noted that initial velocity of the car, that is u, is 0 and its uniform acceleration a is 7.4 meter per second square. For t equal to 1 second, we substitute the given values in the position time relation, that is s equal to u t plus half a t square, which gives distance s equal to 0 plus half of 7.4 into square on 1, which is equal to 3.7 meter. Let us continue with the same problem. How far it would travel in 3 seconds. For t equal to 3 seconds, we substitute the given values in the position time relation, which gives distance s equal to 0 plus half of 7.4 into square on 3, which is equal to 33.3 meter. Now, how long does it take for the racer to travel 7.4 meter? Here, distance s is equal to 7.4 meter on substituting the given values of initial velocity u, which is equal to 0, and acceleration a, which is equal to 7.4 meter per second square in the position time relation. We get 7.4 equal to 0 plus half of 7.4 into t square. This would give time t is equal to square root of 2, that is 1.41 seconds. Let us now continue for the final equation of motion. It relates velocity to the position. We start by solving for the time t in the first equation of motion, that is Vf equal to Vi plus a times Tf minus Ti, or Tf minus Ti is equal to Vf minus Vi divided by a. Now, we substitute this value into the position time relation, that is xf equal to xi plus half of the sum of Vi and Vf multiplied by Tf minus Ti, and by eliminating t, we get xf equal to xi plus half of the sum of Vi and Vf multiplied by Vf minus Vi upon a, which is equal to xi plus Vf square minus Vi square by 2a. This gives Vf square minus Vi square equal to twice of a into xf minus xi. It further gives Vf square equal to Vi square plus twice of a into xf minus xi. This expression allows us to relate the velocity at one position to the velocity at another position without knowing how much time is involved. This function shows the velocity as a function of position, hence it is known as velocity position relation. This is the equation of motion to measure velocity for uniform acceleration. सरलता ਲਈ ਮੰਨ ਲਵੋ ਇਨੀਸ਼ੀਅਲ ਵੈਲੋਸਿਟੀ vi ਬਰਾਬਰ ਹੈ u ਅਤੇ ਫਾਈਨਲ ਵੈਲੋਸਿਟੀ vf ਬਰਾਬਰ ਹੈ v। and let xi equal to x0 and xf equal to x, we can rewrite the relation as v square equal to u square plus twice a into x minus x0. If s is the displacement of the particle, that is x minus x0 equal to s, then general relation becomes v square equal to u square plus twice a times s. For better understanding, let us try to solve some numerical problems. An electron is emitted with a velocity of 5 into 10 to power 6 meter per second. It is accelerated by an electric field in the direction of initial velocity at 3 into 10 to power 14 meter per second square. If its final velocity is 7 into 10 to power 6 meter per second, then calculate the distance covered by the electron. Here, initial velocity u is equal to 5 into 10 to power 6 meter per second. Its acceleration a is equal to 3 into 10 to power 14 meter per second square, and final velocity v is equal to 7 into 10 to power 6 meter per second. On substituting the given values in the velocity position relation, we get square of 7 into 10 to power 6 equal to the square of 5 into 10 to power 6 plus 2 into 3 into 10 to power 14 into s. Therefore, s equal to 49 into 10 to power 12 minus 25 into 10 to power 12 divided by 6 into 10 to power 14. On solving, we get s is equal to 0.04 meter. In our next problem, a forest ranger driving on a straight road suddenly sees a deer. The ranger, who is driving at 11.4 meter per second, immediately applies the brake and slows with an acceleration of 3.8 meter per second square. If the deer is 20 meter from the ranger's vehicle when the brakes are applied, how close would the ranger come to hit the deer? Here, initial velocity u is equal to 11.4 meter per second acceleration, a is equal to minus 3.8 meter per second square, and final velocity v is 0. On substituting the given values in the velocity position relation, we get 0 equal to square of 11.4 minus 2 into 3.8 into s. This gives distance s equal to 17.1 meter. This shows that the ranger would stop 2.9 meter close to the deer. In the same problem, how much time is required for the ranger's vehicle to stop? Using first equation of motion, that is v equal to u plus a t, and substituting the given values, we get 0 equal to 11.4 minus 3.8 t, which gives time t equal to 3 seconds. I hope derivation as well as the application of equations of motions would have become clear to all of you. Let us now summarize what we have learnt so far. Equations of motion can be used to describe a wide range of everyday phenomena. We derived the equations describing the motion of a particle moving with constant acceleration. Do you remember the expression for average acceleration? It is the ratio of change in velocity to the time interval, that is Vf minus Vi upon Tf minus Ti. This can be rewritten as Vf is equal to Vi plus A times Tf minus Ti. For convenience, let the initial time Ti be equal to 0 and initial velocity Vi equal to u, final time Tf be equal to t and final velocity Vf equal to v, then this equation of motion can be written as v equal to u plus at. This is the expression for velocity as a function of time known as velocity-time relation. Next equation of motion can be used to measure the distance the particle move in a given time. For the case of constant acceleration, we describe this equation as xf equal to xi plus half of the sum of vi and Vf multiplied by Tf minus Ti, where xi and xf are initial and final position of the particle. Here again, using the same identification for initial and final time, positions and velocities, and substituting the value of v from the velocity time relation, this relation for position becomes x equal to x0 plus ut plus half at square. This is the relation for position as a function of time, hence it is known as position time relation. If s is the displacement of the particle in time t, then x minus x0 is equal to s and the relation becomes s equal to ut plus half at square. Though the final equation of motion relates velocity to the position. By eliminating time t in the first and second equations of motion, we get Vf square is equal to Vi square plus twice of a times xf minus xi. This expression allows us to relate the velocity at one position to the velocity at another position without knowing how much time is involved. It is known as velocity position relation. Using the similar identification for initial and final velocities and positions, we rewrite the relation as V square equal to U square plus twice A times x minus x0. If s is the displacement of the particle, then the relation becomes V square equal to U square plus twice a times s. So now we come to the end of today's topic. Here's a quick test for you to find out how much you have actually absorbed. Question: define average velocity for uniform acceleration motion. Answer: average velocity is the mean of initial and final velocities. Question: define velocity time relation. Answer: it is v equal to u plus a t. And my question is, define position time relation. Answer: it is s equal to ut plus half a t square. Question: define velocity position relation. Answer: it is v square equal to u square plus twice a s. Question: define